My title is Numerical Methods for Turbomachinery Aeromechanical Predictions. And in order to understand this title, I start directly with the background. So turbomachinery, why turbomachinery? In the first place, we have turbomachines in many places. Around almost 100% in aviation, we have gas turbines. In gas turbines, we have many concerns. One is safety, of course, and also we need to operate in a very wide operating range. And we have to do this with these weight constraints. On the other hand, we have very large use of turbomachinery, in general thermal turbomachinery, in electricity production. And this is, I hear myself, this is around 90%, let's say, we can say we have turbomachineries in energy production. Not only gas turbines, but in general thermal turbomachineries. And one of the important aspects here is the reliability, and then these machines need to work for very large running times. So what happens is that we all have this environmental challenge where we have to have the CO2 emissions low. And for doing this, we can decrease also the fuel consumption. And to do this, we need to have components that have very high efficiency, not only in the cycle efficiency, but also every component should have a high efficiency. So all these changes have led to different modifications in the main components that we can say are the blades of the turbomachineries, or the blisks, or the discs also. And we need to design very highly three-dimensional blades that are having higher performance. Because they're highly three-dimensional, we need to understand this vibration a little bit better than the common flat beam blades that we had before. They tend to be thinner and lighter, also related to the weight restrictions. They're pushed to having less components, so we have less blades, which means each blade has a higher load. And also there's the introduction of a new structure, which is called the blisk, which is an assembly formed from the discs to the blades together. So from one complete piece, you get all the disc and the blade, which means there is no friction damping. And this you will see is very important for the vibration. Also, another aspect is that when there is the use of the alternative fuels, the operating conditions, for example, for power generation can change. And then we need to be able to have reliable operation there. And also a challenge could be working in part loads. So all this together increases the vibration challenges. And this is a deal inside the aeromechanics, which is another word in the title that I have. So what is aeromechanics? So I can simplify this saying that we have a structure. We can say this is the blade, this is the cross-section of a blade, and then we have a flow. So we have flow and a structure, but the structure is not by itself. It has neighbor blades also, which they interact with. And this blade vibrates. This vibration causes a feedback, or let's say an influence on the flow, which creates an unsteady pressure, which can translate into a good thing, which is a damping of the vibrations. But it can also establish in a kind of way that fits back into the system, causing a self-excitation, which is flutter, which is an unstable condition, which is not good. And then additionally, the influence of the vibration of one blade influences itself, but also influences the neighbor blades, and the other way around. We not only have one row, but we have blade rows, and they're not static, but we have rotating components and stationary components. This difference in the relative frame of reference leads to an interaction between both upstreams to downstream blades. And this is related to, this causes blade row interaction forces that can be causing high cycle fatigue problems. And I usually talk here about force response, which I will also talk about this in the thesis. Also, the ideal case is that all the blades are the same, but actually this is not true due to manufacturing tolerances, so I just make a drawing there that the blades can be a little bit different, and this is referred to as mistuning. And the problem with mistuning is that it can cause that all the blades vibrate with different amplitude, and usually you have a higher amplitude than what you want, so the blades with the highest amplitude is the one that is going to fail. So as you see, this is a very multidisciplinary task, which involves structural dynamics, solid mechanics, where we see the vibration, stresses, the fatigue, the material fatigue, and then we usually have the use of finite element tools there. And on the other hand, we have to care about the fluid dynamics, where we consider about the mean flow distribution, the unsteady flow distribution, where we use the computational fluid dynamics tool here. So when we talk about force response, and this is related to the high cycle fatigue problems. The most important thing is to have all the components below the fatigue envelope, or the material fatigue margin, let's say. And this can be shown in the Hay diagram, or Goodman diagram also, where we have a combination of static stresses. The static stresses are related to static forces or mean forces, let's say. It comes from the centrifugal loads, for example, or from the mean flow. And this is here in the axis. And on the vertical axis, we have alternating stresses, which are the ones that are coming from the vibration. What happens is, if you have less blades, you would have higher stresses here, mean stresses. So this point, for example, which could be a critical point on your blade, will move to the right. So this means the fatigue or the alternating strength envelope is reduced. So that's why also predicting the vibration stresses becomes very important. So vibration. How do we determine the vibration amplitude now? So this can be very briefly simplified in that we have a structure. This is the blade. We have an excitation force, which is causing a force or a cyclic force on the structure. And we have a damping, which is contracting the effect of the forcing. So the excitation force can come from blade roll interaction, as I mentioned, and we need to know what is the frequency of the excitation, the distribution of this excitation on the blade, and its phase, and of course its magnitude. And then on the damping side, we have either material damping, which is the damping that every structure has, or we can think about molecular friction, let's say, into the material. We have friction damping, which is due to the relative motion between two surfaces or contact surfaces. And then we also have aerodynamic damping, which is this resistance from the flow due to the vibration. And this is especially important in blisks because we have very low friction damping there. Or we can say we don't have friction damping, or we have only material damping and aerodynamic damping. So, but at the end, we can simplify this and we say at resonance or at the critical position, the amplitude can be said to be equal to the force, is proportional to the force divided by the damping. So on the structural side, what we need to know is we need to know our structure. Here I show a blisk. This is a disc with blades. We have mode shapes, which is the shape of vibration that every structure could have. In this case, it can be represented in nodal diameters, which is this inflection line that you see here, and blade mode shapes that can be bending, torsion, second bending, etc. So every bladed disc or blisk mode shape can be represented in a combination of disc modes or blade modes. But then every structure has a set of eigenfrequencies, and the critical position happens when the eigenfrequency coincides with the excitation frequency. And this is illustrated in a Campbell diagram, which is one of the diagrams important in turbomachinery, where you have in the axis the rotational speed, and then in the vertical axis you have the frequency of excitation, the frequency, let's say. And then the horizontal lines can be the eigenfrequencies of all the structures. And when these ending ordered lines are called ending ordered lines, but they're the excitation lines cross with the eigenfrequency, you have a resonance condition or a potential resonance condition. And then I just highlight one of these crossings. So we not only have one, but we might have, as you see, many crossings there in the operating range we can have. So how is then the blade vibration at different speeds? This is a transonic compressor, and it's actually our test case. I just show here, you see you have blade rolls not only upstream but downstream. This is the rotor blade. And then if you imagine the flow, and then you stand passing through here from inlet to outlet, and then you stand on the blade. If you want to imagine how this blade would vibrate, it would be something like this. At one specific speed, one mode shape will react at resonance. And then this is a blade mode shape. You see it's a specific shape with a specific amplitude, which is this peak here, and at a specific frequency. But if I move to a different speed, then I see another mode shape with a different frequency with a different amplitude. So what I need to know is how this amplitude is. So this is about the structure. So the other thing that we have to know is the excitation force, and it comes from the aerodynamics. In this case, the most common practice is to use computational fluid dynamics. What happens is that you need to model a very large mesh because you need to account for stages. It's not only one row, but you need to account for the stages which interact with each other. It is an unsteady calculation or time marching. It could be very small if you manage to reduce your domain and use specific boundary conditions in the interfaces that allow you to model only one sector. But it can be very large also, because you can model multi-stages. You can have very advanced models to solve the turbulence, for example. And then you would have to model the 360 model. So this could be very, very, very expensive. So there is a different reduction methods to assess this in an industrial environment, let's say. One of the most common ones is the chorochronic methods, which assume the flow is periodic not only circumferentially, but also in time. So then with that, you reduce the domain to one single passage. There are other methods, which is time inclination method that allows to change the governing equations and introduce like a fourth dimension where the interfaces, the time is inclined. But I don't talk too deep about this because I'm not, but I just want to show there are other methods. And then a third method is the scaling, where you actually not model the complete full model, but you model a sector. And sometimes you cannot have a specific matching blade row from the upstream to the downstream because there's a difference in blade counts that is not an integer number. So you would tend to modify a little bit the blades or scale them to match them. But then, how accurate is this? This is one question that I ask, and I also assess this in my thesis. And then the third part, or the missing part here for a blisk, would be the aerodynamic damping determination. And where does it come from? The picture that I show here is just a bunch of blades vibrating. As you see, they have a specific mode shape. But they have a specific interbraid phase angle. And this interbraid phase angle is related to the nodal diameters of the structure. But then what you see is that you have a frequency, an amplitude, a mode shape that could be the same, but an interbraid phase angle. And this is the ideal case, is when all the blades are the same. So what you're interested in, what I show here also is these colors here, is the pressure on the blade changing due to the vibration. And this is actually what we need to predict. And this is comes from usually from time marching solvers or CFD calculations. So we need to predict for a specific frequency and mode shape what is this damping produced at different interbraid phase angle. And then we introduce here the stability curve. And what happens is that at some interbraid phase angles, the damping can be negative. And this is it means that there is a risk for flutter where you have an unstable condition. But if we have a positive damping, this is very good for us for the force response because it would damp our vibrations. So how do we determine this? One approach that is very useful is a single degree of freedom approach, where the blade, its model, has a single degree of freedom, and this is the ball here. And then we say the blades are connected not only by the structure, or not by the structure necessarily, but by aerodynamic springs. These aerodynamic springs come from this vibration of the blades and the communication between them. So this is usually called aerodynamic coupling. And we call this system that we work in the influx coefficient domain. So we say that the influx of different blades can superpose linearly. And this is valid for small perturbations. There are some assumptions here, is that when we do this only when the blades vibrate to a specific mode, and we assume no blade mode family interaction, and then we assume the mode shape don't change. So this is most often the case where we have low damp blades, and it's a very high computationally efficient method. So then if we solve this dynamic system with aero coupling, we can get an aerodynamic damping here. So if this damping becomes negative, we have a flutter risk when the structural damping that comes from friction is not high enough, such as the sum of these two is less than 0. I also talk about at the beginning about mistuning. So what mistuning does is that, well, first of all, due to manufacturing tolerances, wear or foreign damage, object damage, not all the blades are exactly the same. So ideally, you would have for a specific resonance, you would have a peak here. This is the blue peak. But if you have mistuning, it causes a frequency split between the blades. And then also it creates an amplitude magnification. And this is very detrimental. And then you don't know what the amplitude magnification would be. You don't know how the frequency mistuning is before, because you don't know, it can be distributed in different ways. And you might not know the strength before when you're in design. The other consequence of mistuning is that it has an effect in the aerodynamic damping. And it has been studied that the minimum damping that you can get the minimum damping in your stability curve can get increased, such as you actually can move away from Flutter 1 unstable mode. But the other thing that we have to think is not only the minimum damping changes, but the highest damped nodal diameters can also come down. So in the force response, we also have an influence of this damping depending on mistuning, if we have a major damping from the aerodynamics. So how to deal with mistuning? Well, I mentioned that you have to do statistical studies because you don't know what is your distribution pattern of mistuning or your strength. So if you do the full element model, this is very expensive, so you could not really do this in a feasible time. So many reduced order modelings are used. I list here the most common ones. They deal with they're called model decomposition and component mode synthesis. These two, they solve for they managed to reassemble the complete blisk by basis of mode shifts from the tune case and with some perturbations. But there are also a large study about the structural effects of mistuning has been assessed, especially with these methods. But then lately, the aerodynamics have been included. And for this, most of the methods that have given us an understanding is called the fundamental mistuning model and also the asymptotic mistuning model, which take the blade also has a single degree of freedom coupled, and then they can see how the mistuning could affect the force response or the flutter. And then I talk here about a third method, which is a static condensation technique, which is Kuyan, and I also use this in my thesis. And in this case, it's based on the static deformation of specific master nodes. And then we require the selection of master nodes, and then it depends on the number of the accuracy depends on the number of master nodes we use and on its distribution. But the good news about this method is that it can be a little bit more expensive than the single degree of freedom, but it also allows for large mistuning. And also, it's compatible with some methods that I will explain later. And then another subject that I treat here is mode interaction. So if you see the peak response of two resonant frequencies for the same structure, you will get, here's the frequency, here's the amplitude. Then you can get two specific mode shapes like that. If this gets closer, you will get a response that is a combined response, something like that. So this means that the modes can interact with each other. This can happen in case of very light twisted and highly loaded blades. There is some interaction between the mode families. It can be that in the same blisk you have modes that could respond to one mode shape, one blade that can respond to one mode shape, and another blade that can respond to another mode shape, due to very high influence of the structural and aerodynamic coupling and mistuning. So it has been studied before, that especially for damping, for flutter analysis, that when you have a mode interaction, your aerodynamic damping predictions can be influenced. So you can no longer model the modes as a single degree of freedom. And you need to account for mode interaction. So how is then the aerodynamic aeromechanical design chain after all this background? Well, we can think that first we have the design specifications, how we have one aerodynamic design, which is optimized with very high performance. Then we aim to go into the aeromechanical loop or numerical loop, where we only have our computer and we try to do all this analysis, both for force response and stability analysis. We have this we do also this interaction between the manufacturing geometry and the design geometry, which is called the hot geometry. And then we ask ourselves, are we okay in the sense of the flutter and also with the fatigue margins? If we say no, we have to go all the way back to the beginning, and this loop is very costly, even in the numerical loop. But then if we say yes, we can continue, and then we go to the engine tests. I just presented a Rolls-Royce engine there. And then if we all the engines are tested. If we ask the same question, and this design is not good, then this is super more expensive. So you have to go all the way back to the beginning, or maybe you can do some arrangements without having to redesign, but you have to do a kind of loop that is very expensive. And then, but anyways, if this is okay, then you go and then you put your engine on the plane, and then you ask yourself, is there any failure now that the plane is flying? If it is yes, very good, no problem. If it is, if it is not, no problem. But if there is a failure, this is the critical point here, because what do you do? So what I want to say is that we have to put a lot of effort into having the best prediction tools at the very beginning to allow going through this change in the most optimal way. I have just a citation, which it has some years, but I think still applies, that 90% of the high circuit fatigue problems are covered during the engine development. But the 10% that remains stands for the 30% of the complete engine development costs. So there is a lot to do with these aeromechanics problems. So my objectives now. Very late, but I think now it should be clear. The main objective is the development, validation, and application of a numerical tool for aeromechanical analysis, and this is very general. So inside this objective, I have some sub-objectives. First, the development and validation of the tool, considering mistuning, which, as you've seen, has important parameter. Then I go and I determine a specific or a number of numerical uncertainties in the aeromechanical chain. Not all of them, but some of them I assess. And then I apply this tool in an industrial BLISK, and I compare with experiments. And I see if I run my chain once, how accurate this is. And then I also propose a new method where I include the possibility to have mode shape modification. And this is targeted for the future applications and not maybe to the urgent needs, but also looking forward for new design perspectives. So I will start with first objective, the development philosophy. The tool needs to be user-friendly in the sense that any design engineer should be able to use it. It should be open for industrial standard tools, so we're not redesigning CFD or FE. So we allow the industry to use their standard tools. And then this is an aeromechanical integration tool. It should be open to emerging methods, because this is always, we need to evolve, so we cannot close the tool. And then it should have outputs for further stress assessments, because there might be many ways to do the fatigue analysis. So we're not going into details there, but we should leave open for further stress assessments. So this is the overview of the tool. You have on one side finite element solvers that provide the structural parameters, which are mass and stiffness, and also static stresses if you in the future want to do stress analysis. And on the other side, we have CFD solvers that provide unsteady forces due to blade roll interaction. We transform this into the harmonic domain, and then we map the two solutions together in a mapping process here. We allow to import structural damping in the sense of linear damping, so it's in terms of the critical damping ratio. And then, but we also allow to introduce the aerodynamic damping, either has a single value or has an aerodynamic spring. Then we introduce a reduction model. In this case, it's a Gaussian reduction model, where we can assess mistuning analysis. Then we integrate all this, and then on one hand, we can give the answer about what is the stability of the system. And on the other hand, we produce vibration amplitudes that can be further processed for a Hague diagram and then final fatigue risk assessment. In summary, the aroma capabilities are for force response and stability, including mistuning, both capabilities for structurally coupled and aerodynamic coupled analysis. And then the main outputs are the stability curves and the frequency response. The current programming language is MATLAB, and then we can discuss later why we have this. This is a brief validation of specific aspects of the tool. Here we have very simplified models, and we just solve in aroma what we solve in a regular finite element model. So here, if we put a complete plate disk, let's say, with some blades, we can introduce one blade which has a specific density difference, and then I just show the force response obtained by doing this in aroma with a full model or y-ANSYS. So this is just a check that the tools are doing the correct thing. So you see the frequencies are responding to, they're a little bit different, and the amplitude is also different. The mistune, the validation for the mistune, the reduced model, is just by a cross-validation between simulating a mistune case with one blade mistune and doing the reduction model, and compare with the complete full model with the blade mistune. So here you would see the one blade, this blade responding to a specific frequency, and the other blades responding to similar frequencies with different amplitudes. And then this is just a cross-validation between the reduced model and the full model. So this is to show this is a pre-validation before we assemble the complete BLISK into these models. So second objective, determination of a number of numerical uncertainties in the aeromechanical chain. For this, we have the test case. It's a Hulda transonic compressor. It comes from designed by Volvo Aero, and it's aimed to be the future fan fighter engine. It's a future fan fighter engine demonstrator. It's a very highly loaded blade, and the rotor blade has a very three-dimensional design, which is good for this application. It has 5 front frames, 15 VIGVs, 23 rotor blades, 51 stator blades, and 8 outlet guide vanes. So the number of numerical uncertainties we chose, on one hand, we have the scaling, a technique for aerodynamic forcing calculations using CFD. We also have what would be the accuracies when we just transfer the data from CFD to FE meshes. And then the third is, if we use Gaussian reduction, how accurate this is, and which guidance should we use to have an accurate model. So for the first one, the scaling sensitivity, we have, I just briefly mentioned this again, is to scale the blade rods for spatial periodicity. So we do this by maintaining solidity, which means the performance or the steady state or the loading should be preserved the most possible. This doesn't assume any temporal periodicity, which means that if there's shedding, this kind of models could also determine the frequency of perturbations due to vortex shedding. Also, the advantage of this is that there is no need to any adaptation of boundary conditions. Any code, commercial code, could be used, and we just update the domain, and then we do our simulation. But the problem is that it changes the frequency, the force magnitude, and due to this geometry modification. So we want to know how accurate that is. So we chose, on one case, our validation case is to model the 360 model or full model without any scaling. And then we chose 4 other cases where we scale the rotor and the stator blades. In here, we only include the rotor and stator. And we use 3D and CD Navier-Stokes equations using an in-house code Volsolve from Volvo Aero. There is no tip clearance, and this is done at design speed with choke conditions. So we have, I just show here, there is an overall scaling ratio, which I also define in the thesis, which gives us a sensitivity of how much the system is scaled. The variable that we're looking at is called generalized force. It represents the mode excitability. In this case, the generalized force will tell us some information about how the unsteady force is distributed over the blade, something like this. This is the harmonic force distributed over the blade, and how its relation with the mode shape. And this we check on the rotor and on the stator blade. So this is the results on the rotor blade. Here are the generalized force for all 28 mode shapes. All these color lines are the different scaling cases. And then what you see here is that in general, all the cases predict the trends of the excitability of the modes. And then you could kind of rank with this method. But then in general, we can see that this is if we take the root mean square of all these, the deviations of all the mode shapes for the rotor here and to the stator, we can see there is a linear trend with increasing scaling with the accuracy. And here we see it goes down again, but in general, okay. In general, there is, for the first, when we increase the scaling, it gets more inaccurate, let's say. So we conclude there that when we have around 5% of overall scaling ratio, the results of the generalized force could be around 10% to the full model. And then the third part in this section is the effect of the CFD-FE mapping. So for this, we have 2 cases. On one case, we can take the CFD force and put it into the finite element model. For this, we can take the closest node and put it there. And then the other way to do it could be to have the mode shape map into the CFD mesh. In this, we use a weighted average, so there is no need to move forces around there. So what we have done is to take 2 different excitation conditions. These are the CFD forces, and this is the finite element mode. And then when we map these kind of forces into this mode shape, we get a lower sensitivity of the process. And then when we have a force where the high perturbation is not close to the high excitation or the high deformation of the mode, we have a much higher sensitivity. So for forces that are, for very localized modes, the mapping method that you use should be very good. That's pretty much the conclusion, because it's highly sensitive to that. And then the effect of the Gaussian reduction. For this, we have created a matrix of studies. One, in the axis, you have a different distribution. 10% would be all the nodes distributed close where you would expect the high displacement of a mode. And 100% is not caring about any displacement. And then from 2% of less nodes and then more nodes, let's say here. This is what it means. So there is kind of like a matrix to see what is the effect of the number of master nodes, but also what is the effect of the distribution. And then we want to know what is the effects in the frequencies and mode shapes. So for this, I showed briefly these results. Here you see the frequency error with respect to the full model. In the axis, you have the distribution, and then the y-axis, you have the number of master nodes. So what you see is that the blue happens, it's the best case, let's say, for mode 1. So it suggests that, of course, if we have higher number of nodes, we have a better result. But also it says that if you have a highly distributed set of master nodes, it's also very good. So we can say that if we want to have the minimum number of master nodes, maybe here 4% here, and have the minimum error, we would have to have it very evenly distributed. So that's what it says. And then I just show similar happens with the Mach number, which is vice versa. So the red is good in this case. And then also that the sensitivity of the accuracy is, I mean, you have the lower modes are higher, more accurate than higher modes. So we go to the third objective here, application of an industrial base and comparison with experiments. We study here one specific crossing. This is the mode 4, excited by the 15 Ngora that comes from the 15 VIGBs upstream here at the 13,200 RPMs, which is not designed, but we chose this because in the test it was a high amplitude case. And then it's excited at the nodal diameter 8. So this is the Campbell diagram. This is the finite element mesh that we use, and then we did the CFD calculations using CFX. You have we have two cases where nominal cases when the VIGB has a 0-degree angle, and then positive 30-degree angles of the VIGB. So this translates into two different excitation conditions, and then we're going to look what is the effect of this on the rotor blade, which is this one here. So for the steady-state results, we have the speed lines of both cases. This is for the nominal case, for the 30 VIGB case, and this is a test speed up. So we have done this using a mixing plane interface, using the K-epsilon turbulence model, and then with inlet boundary conditions from the test data. We have done this, the steady state we did with two solvers, CFX and Volsol, and there is no tip clearance. And then what we got here is that at the same mass flow on the test, the pressure ratio of the speed line with respect to the test was around 1.5% different. The aerodynamic forcing was done also with 3D on steady Navier-Stokes with no tip clearance using the K-epsilon model. And we have used scale case here, as we mentioned before. In this case, we chose 1/5 of the full annulus. And the scaling was as much as almost 10%. So what you see here is when we do a Fourier transformation of the forces, this is the axial force, we see the major peak from the VIGB. This is the 15 Ngora, but we also see some lower peaks from the other harmonics there. So what we see is that the integrated force is 5 times higher for the 30 VIGB case than to the nominal case. And this is due to the increased effect of the viscous and potential effects due to the VIGB put in a different position. But then, this is the integrated force, but when we look at the generalized force for that mode, it's actually 15 times higher. So for the 30 VIGB case. The aerodynamic damping was performed using a 3D linear Navier-Stokes solver, also in-house code from Mayorca. We have produced the stability curves here. This is for the nominal case, and this is for the 30 VIGB case. So here you see at different interbraid phase angles or nodal diameters, you have a different damping ratio. And then the damping present at the responding mode at the nodal diameter A is highlighted here. And then what I show here is what it was predicted from the test. The tests are from tip timing data, which means that we get a specific frequency peak signal from every blade. And then it was a single degree of freedom approach was used to estimate the damping per blade from this resonance peak, which means that we get a different damping per blade, which can be argued because we are having here system damping, not a damping per blade. But anyways, if we do the average of this test damping, we get this point here and this point there. So it's actually, we're over predicting the aerodynamic damping. But the scatter between the damping between the blades is these vertical lines that you see, so it's very, very large. So for the nominal case, we can say we're inside the range, but for the other case, we're not inside the range. So that's why I say we can say the trends are captured because the nominal case has a higher damping than the nominal case, like in the tests, but also the scatter from the nominal case on the test is so large that we could even doubt that the trends are captured here. So another analysis that we did is the mistuning influence on damping. So this was a parametric study. We took a single degree of freedom approach, aerodynamic coupled, and then here when you solve that for the tune case, you get a very nice circle here. These are the frequencies. This is the damping ratio. Each point is a different nodal diameter. The difference in frequencies in the nodal diameters is due to the aerodynamic coupling. And then when you introduce mistuning, we introduce it by the measuring, by introducing a different frequency in the single degree of freedom blades. And then we just break this nice circle. But the effect is that the minimum damping is increased and the maximum damping is decreased and tends to the average. But even if we put a very large, the largest mistuning in the test, the maximum decrease of the positive damping is 7%. So it's not enough to say that mistuning is what is causing our tune case to be higher. And then another analysis is to do a mistuning analysis on the amplitude magnification. So this is no aerodynamic coupling, only the structure is here. We use a reduced model there. And then we import into Aroma 3 different sectors that and combine into 100 random distribution cases. And then we achieve a kind of frequency difference of 0.4%, which was measured on the test. And then doing such kind of analysis, we can get an amplitude magnification of 1.38 at the 99% confidence level, let's say. And in the test, the values were 1.16 or 1.35. Finally, if we put all this together, these are the red one is the test results for the nominal case and the 30 VIGB case. And this is black lines are the tune case. And then the blue lines are if I just scale this by amplification factor. So it's a scaling thing due to mistuning. So what we see here is that both cases are under-predicted. And the prediction is between 30 to 30%, 70 to 30%. We can discuss this also later, why. New method for aerodynamic coupling analysis, or aeroelastic couple analysis with allowing mode modification. I introduced here the multi-mode least square. And the key features of this is that instead of having the single degree of freedom blade, we have a complete finite element mesh. And this allows us to have mode shape modification, and it's not restricted to the in-vacuum modes. This model is compatible with the Guyan reduction applied in the structure. And then we achieve mistuning also by importing different blades in the system. And the model requires the solution of the CFD aerodynamic forces outside the model. This allows a very high generality for design parametric studies. So what is the physics behind, or the thinking behind, is we want to produce aerodynamic influence coefficient matrices. So if you think now that I can represent a blade in only 3 points, 3 nodes here, and then if I oscillate one of the nodes there, this one, for example, I will produce a perturbation on the flow which has an influence on itself. I can represent this as an aerodynamic spring on itself or to Earth, let's say. The same vibration of that node would have an influence on the neighbor node and on the other one. But then if I oscillate, the middle one is the same. I produce an influence on the other 2. And the other one, the 3. So what happens is that I can represent the influence of this blade on itself by a set of springs of the specific nodes. So this translates into an influence coefficient matrix that would be 3 by 3. And I can say this is the influence coefficient matrix of this blade on itself. So how do we couple the other blades? So if I oscillate this node here, it would also have an influence on the neighbor node and on the other one and on the other one. If I oscillate the middle one, the other 3 springs appear. If I oscillate this one, other 3. So here, again, I can produce an influence coefficient matrix 3 by 3, which is the influence of blade 0 to the neighbor blade. So I call these springs, or these matrices, the aerodynamic stiffness and the aerodynamic damping matrix in the influence coefficient domain. So how do I get this matrix? That's the question. Because I cannot oscillate one node in my CFD. It's very hard to imagine. So we assume as the static behavior, let's say, we want to get aerodynamic forces equal to an aerodynamic stiffness that would represent any motion. So if I oscillate, if I have a motion, this aerodynamic stiffness would tell me what is the aerodynamic force produced. So this is my influence coefficient matrix. It is based in this, that if you have the displacement of one node, you can represent this as a linear combination of mode shapes on that node. And this will give you an approximate solution. This I call the generalized coordinates, these coefficients that you multiply each mode. In the same way, the responding aerodynamic forces can be represented as a linear combination of the modal forces due to the oscillation of modal vectors in the CFD. And then this would be equal to my original equation. If I minimize my approximation to the best solution, it will be the derivative of that equal to 0. You do all the math, and then you get to an aerodynamic stiffness matrix, which is represented in terms of the model forces vector and the model displacement vectors. So in the same way that I did the stiffness matrix, I did the aerodynamic damping matrix, but the only difference is that now I have to include a frequency content in the damping matrix. In this case, would be related to the frequency of oscillation of the mode. So if I produce this model, and I have applied this to a force response calculation, aerocouple, and with mistuning, so of two specific modes. So what you see here is that if I mistune that, and I want to see what is my amplitude magnification with respect to the tune case, I get some nodal diameters that have a lower amplitude and some others that get a higher amplitude. And this is related to two things. One hand is the amplitude magnification, and the other thing is that there is a damping varying because I don't have any other damping included there. So this is why this V curve in mode 2 and mode 3. And additionally, the MLS, or this multimode least square model, is not done mode by mode basis, but I can do a frequency sweep, and if the two modes interact, I can see it there. So I just show here the difference, for example, of the influence of mode 3 and mode 2 by this small difference when I compare to the single degree of freedom only using mode 2. And then if I dramatically increase the damping and I made the blades actually change the frequencies in the same resonance, I will get a mode shape something like this. Some blades responding to, for example, this is torsion mode, and then two second bending. And yeah, exactly. So here you would have, in this point here, you will have, these are the response of different blades. You have some blades responding to the torsion mode, and then some blades responding to second bending, and this is a combined mode in the sense that the blades have different mode shapes. So now the last question that I ask now is, can we predict the aeroelastic behavior now from any arbitrary mode, not knowing my in-vacuum mode? So yes, if I can create a huge database of mode shapes and associated unsteady forces that can superpose linearly and produce any mode that I want. So that's one hand. And second, if I can fit, it depends also, because if I want to model any mode shape, I can also say I want to predict any frequency range. So I need to have a model that allows me to fit the frequency on the range that I want. So I have done a demonstration with this. So I took the first 7 real modes of the blade that I know, and I know from my finite element. And then I create different modes, and I try to predict, without having the input of these modes, what is the response or the elastic response. So for this, I use the Guyan principle to produce a database of mode shapes. So I select a set of master nodes, which are highlighted here. And what I do actually is you can imagine that I pull one node at a time. And due to static deformation, I create a specific mode shape. So then if I pull it in one direction, I get a deformation. If I put it in another direction, then I can produce a database of nice shapes like that. And then if I superpose them linearly to fit by least square to fit my real modes 1 to 7, I get an error, of course, because I don't have an infinite number of mode shapes, but I get an error that increases with increasing mode. But this error is of an accuracy when we look at the Mach number or the Mach assurance criteria number from 2 to 12%. So what I do is that now I go to the CFD, I take all my arbitrary modes or these Gaussian modes, and I oscillate them. At what frequency? That's the question. It depends on the range that I want to predict. So if I want to predict from the 1st to the 7th frequency, I now chose to oscillate in 3 different frequencies. And then I can use this database in as many, in the specific frequency range that I want. The drawback is that now I have to simulate 128 linearized calculations. Okay. So the frequency considerations, I mean, this is we can just take the aerodynamic influences there. Now you see we can only fit the frequency to a quadratic function, only the mass and the stiffness. But the aerodynamic damping is only related to one frequency, which is linearly related like that. So if we oscillate our mode shapes to 2 different frequencies, we can fit them nicely, but the damping is limited by the linear fit. And this is represented in this chart. These are the different influence coefficients. If I take one mode and I oscillate it at different frequencies, and I decompose this in the influence coefficient domain, I can get that the real part, I can fit quadratically with these dashed lines, but the damping part, I can only fit linearly. So if, for example, the influence coefficient of blade 1 is not linear, like that, I cannot fit that in the frequency. So I'm limited to a specific frequency band. So this is my reference case. This is the stability curve per mode. So this is the first real modes oscillating them with the specific mode shapes. And I'm interested in seeing what is the stability curve amplitude and the mean of this to compare with my MLS. So this graph is just the stability curve amplitude here from the real and the predicted one. So if I oscillate my Gaussian modes into the lowest frequency range close to mode 1, I get a good match there, but not on the other modes. If I do the other way around, I oscillate my modes to the highest frequency, I get a good match of the higher modes, but not to the low ones. So, summary of the observations in this part. It is possible to represent the responding modes from a database of arbitrary modes, but it depends on how well your database of modes is represent the mode that you want to predict, and also how wide your frequency range is. Recommendations is to then include a real mode, and then some basis of perturbation of that mode. So you don't have to model 128, but some basis of perturbation that allows you to fit to the expected perturbations that you have. And then also, it's the same. I mean, if you have a small frequency range of different, then you oscillate to that frequency, and then maybe to a neighbor frequency to that. Conclusions. Conclusions 1. Then aeromechanical tool has been developed with considerations of existing methods and also some newly developed methods. The numerical uncertainties that we studied, we said that the scaling actually could lead you to a aerodynamic forcing impact about around 10%. The mapping method can also, even if you sometimes disregard, this can actually have a sensitivity between 3 and 8%. The reduced order modeling, it depends now, in this case, in the master nodes selected, but there are some recommendations given. We'd recommend to have distributed master nodes if we don't know our mode shapes, how they're, if we want to predict any mode shape, let's say. Then a standard aeromechanical chain procedure resulted in under-predicted amplitudes of 30 to 70%. But this, I need to highlight here that this is one run, and there you can optimize this, of course, but if you don't know anything about your model and you take the most simplified cases and tools that you have and you run it, how far off you are. And then, of course, you can loop in and try to improve this. Higher excitation levels seem to be better predicted in this case. Numerical statistical analysis could give us an idea of what is the amplitude magnification expected due to mistuning. And then, also including mistuning effects on the aerodynamic damping, since this is a bliss, can increase the accuracy of the final results. But we can overall say that the order of magnitude of aerodynamic damping, forcing, and vibration amplitude were captured. And some trends, yes. Conclusion 3, a new method is proposed that allows you mode family interaction or mode shape modification. And the applicability of the method is targeted to parametric studies when mode shape could be altered. And this could be due to either coating, damping, mistuning, or because you wish to do a stiffness modifications for some reason, and you want to see what is the effect on the aerodynamic damping. Recommendations for future work. Can be introduced new reduced models. For example, the asymptotic mistuning models are the fundamental mistuning model to have an increased flexibility in the mistuning analysis with large models. The comparison of the aeromechanical predictions for other operating points and different machines to be able to conclude about these uncertainties. Refining the calculations, of course, doing a more accurate CFD calculation, including, for example, shedding or tip clearances, etc. Extension to the fatigue risk uncertainty in the stress assessment. So go all the way to the fatigue risk, not only to the complex amplitudes. Also, investigating more how can we better compare our aerodynamic damping with tip timing test data. And, of course, applying the MLS into a parametric design and translating aroma to a different language. Because there are some, we don't need to be tied to a license of MATLAB if we want to use this in an environmental, in any industry or in the future. And also we could have more flexible management of memory. And finally, I just want to give an acknowledgement of how many people were involved in this thesis. First of all, it was Damian Vogt was my main supervisor. Mr. Hans Martinsson from Volvo Aero, he was my industrial supervisor, and of course Torsten Fransson is the head of division and also involved in all the papers that I produced. So the first 3 are the co-authors of all the papers in this thesis. Also, we had a master's student, Jesus de Andrade, also working for one of the papers, and Klaus Andersson from Volvo Aero, who also gave us some feedback about the test data. And this project was financed by the Turbo Power Consortium, where the Swedish Energy Agency, Siemens, and Volvo Aero are part of it. And of course, this was promoted by the Swedish Defense Procurement Agency here in Sweden.